This 100,000-ton cruise ship is 20 stories high and is being hit by 30-foot waves. It will tip as much as 30 degrees to one side, but never fall over. Meanwhile, ships full of nothing but air can be capsized in calm seas. So, what's the secret? It's not luck. It's physics and engineering and technology so clever it will blow your mind. Let me prove it for you. The secret starts with something you can't see: ballast tanks. These are massive compartments built into the bottom and sides of the ship's hull. And here's the genius part: they can be filled or emptied with seawater on command. When a cargo ship unloads all its containers at port, it suddenly becomes dangerously top-heavy. The ship rides way too high in the water, the propeller and rudder barely stay submerged, and in rough seas, it could roll over. To fix this, the crew pumps thousands of tons of seawater into the ballast tanks. This lowers the ship's center of gravity and brings it back down to a safe depth. A fully loaded container ship doesn't need much ballast because the cargo weight keeps it stable. But an empty ship? It might carry 40,000 tons of ballast water. That's the weight of 20,000 cars worth of seawater just to stay balanced. The system works like this. Sensors monitor the ship's balance in real time. If the ship starts listing to one side, maybe because waves are hitting from the left, the computer automatically fills ballast tanks on the right side to counteract it. It's constantly making micro-adjustments you'd never notice as a passenger. Modern cruise ships have dozens of ballast tanks positioned strategically throughout the hull. By pumping water between tanks, they can adjust the ship's trim, whether it's tilted forward or back, and its heel, whether it's tilted left or right. This keeps the ship perfectly level, even as passengers move around and cargo shifts. But ballast tanks alone aren't enough when you're dealing with massive ocean waves. That's where stabilizer fins come in, and they work exactly like airplane wings, except underwater. These are massive retractable fins that extend from both sides of the ship below the waterline. On a large cruise ship, each fin can be 15 to 20 feet long and weigh several tons. You never see them as a passenger because they're hidden beneath the surface. Here's how they work. When the ship starts to roll to the left, sensors detect the motion instantly. The fin on the left side tilts downward to create lift, an upward force that pushes that side of the ship back up. At the same time, the fin on the right tilts upward to create downforce, pushing that side down. It's all about balance. The system is gyroscopically controlled with advanced sensors and hydraulic systems that adjust the fins dozens of times per second. The fins are constantly moving, constantly compensating, always working to keep the ship level. It's like having invisible hands under the water, fighting against the waves. The crazy part? These fins can reduce rolling motion by up to 90% in rough seas. A ship that would naturally roll 20 degrees might only roll 2 degrees with stabilizers active. That's the difference between dishes sliding off tables and a comfortable dinner. Modern fins are retractable. They fold back into the hull when not needed. This reduces drag and saves fuel when seas are calm. It also prevents damage when docking because the fins need clearance on both sides of the ship. There are two types: active stabilizers that are computer-controlled and constantly adjusting, and passive stabilizers that are fixed and just create drag to resist rolling. Almost all modern cruise ships use active systems because they're far more effective. Now, here's where physics gets really interesting. Ship designers obsess over something called the center of gravity, basically the point where all the ship's weight is concentrated. For a ship to be stable, its center of gravity must be below the center of buoyancy, the point where the water's upward push is concentrated. If these 2 points get out of alignment, the ship becomes unstable and could capsize. Modern cruise ships have incredibly wide hulls. Some are over 200 feet wide. This width spreads the weight out horizontally and lowers the center of gravity. Think of it like a pyramid. Wide base equals stability. Everything heavy, engines, machinery, ballast tanks, fuel, is installed as low as possible in the hull. The passenger cabins, pools, and entertainment areas up top are relatively light. This keeps that center of gravity down near the waterline. When loading cargo ships, computers calculate exactly where every container must go. It's not random. Heavy containers go on the bottom and center. Lighter ones go up top and toward the edges. Get this wrong and the ship could literally flip over. It's happened before. The hull shape also matters. Modern ships have a bulbous bow, that weird bulge underwater at the front. This actually improves stability by modifying how water flows around the hull and reducing resistance. There's a measurement called metacentric height that naval architects use to calculate stability. I won't bore you with the math, but basically, the higher this number, the more stable the ship. Cruise ships are designed with a metacentric height that ensures they'll self-right, even if tilted 30+ degrees. So with all this technology, how do ships still capsize? Rogue waves, massive walls of water up to 100 feet tall, can overwhelm even the best stabilizer systems. These are rare, but when they hit, no amount of technology can stop the physics. The other danger is free surface effect. If water gets inside the ship and sloshes from side to side, it can amplify rolling motion instead of dampening it. This is why pumping out flooded compartments is critical in emergencies. Modern ships have sophisticated damage control systems. If flooding is detected in one compartment, watertight doors automatically seal it off to prevent the water from spreading. Crew can then adjust ballast in other tanks to compensate. But the bottom line, when ships capsize, it's almost never because the technology failed. It's because the ship was in a situation the technology couldn't handle, usually due to human decisions. From ballast tanks constantly adjusting to stabilizer fins, fighting waves dozens of times per second, to hull designs perfected over centuries, ships don't stay upright by accident. It's a symphony of physics and engineering, working 24/7 to keep hundreds of thousands of tons of steel stable in one of Earth's most unpredictable environments. What surprised you most? Drop a comment and subscribe for more.